Oh, good. So last week we spoke a little bit about what object detection is. We spoke a little bit about the RCNN family, intersection over union, and non-maximum suppression. Let's just go back quickly and see these things again, and then we will go visit the last part of today's lecture or this week's lecture, which is YOLO. So we said that the main difference between object detection and classification is instead of just predicting that there is an object in the image somewhere, object detection aims at finding the exact location of that object inside the image. So here, for example, we have multiple cats and we know exactly where their location is. As you can see, they are overlapping each other. Can somebody tell me what the intersection over union between these two should be? Between the two cats. Just a guess. Of course, it's not going to be an accurate number, but
Half part of both cats, maybe.
yeah, so it's around like 30% or 25%. So with non-maximum suppression, keep this in mind. So again, as we said, we will be trying to predict the location of the objects that we find in the image, as many objects as there are. Applications are endless, as we said, vehicle counting, facial detection and recognition. So the facial detection part is easy because it's just detecting an object. And the facial recognition part, not sure if you guys did this already or, yeah, let's just confirm. Did you guys do this already or not? Facial recognition.
Yes, for me, I never am doing recognition.
Okay, nice. So for those who have not done facial recognition, probably we will talk about it like in the end of this lecture. And the final thing, which is another example, is parking lot monitoring. We spoke about the most basic algorithm, which is just a sliding 2D CNN. We spoke about how to improve it in terms of speed and the algorithm that is being used to propose the, like, let's say, more optimal shapes and sizes for the objects of interest or regions of interest, which is selective search. We also spoke, as we said, about intersection over union and how it is used to convert, not sure if we did that, but it is being used to convert an object detection task into a classification task. Probably we still didn't speak about this part yet. We will speak about it hopefully in the end of the lecture. And we spoke about non-maximum suppression and how it can be used to improve the results of object detection models. Example of these object detection models is the RCNN family. And the RCNN family, as we said, started with a very basic example of just selective search, followed by a CNN applied on each one of these selective search regions. Important thing to note, conversion from selective search image to a exact same size image that goes into the CNN. The problem of RCNN was it takes too much time. The problem of taking too much time comes from the passing on the CNN like 2,000 to, let's say, 1,000 to 2,000 times, right? Fast RCNN is the improvement of RCNN, and the main thing that they did was we no longer apply selective search and then send the image through the CNN. What we do is a very simple technique. First, we take the image, pass it once through the CNN, and then we apply the selective search and do a mapping from the selective search region to the region of interest inside the convolutional feature map. So we're no longer applying the CNN 2,000 times, we're applying the CNN once, and then mapping the 2000 regions into their corresponding 2000 regions in the convolutional feature map. So this is just a direct calculation. And then from this location, we must apply first ROI pooling, and then a couple of fully connected layers to do the classification and regression. As we said, the mapping from what selective search has predicted or selective search has proposed to the actual region that will go into the, what is it called? Into the ROI pooling is being done through a simple division based on the size of the input image and the size of the feature map. So if the feature map is 16 times smaller than the input image, just divide everything that selective search gives you by 16. If it is 8 times smaller, divide everything by 8. If it is 32 times smaller, divide everything by 32. So it's a direct mapping. It takes 0 time, unlike before where it used to take like 47 seconds. And now, did we speak in detail about ROI pooling before or not yet? In the last lecture. Let me set up the iPad maybe, and
I think we're speaking about it in the end of the lecture, but I remember something about it.
okay, that's nice. So let's just give an example about ROI pooling in real life. Let me add the iPad because this will need a lot of drawing. And this is a very interesting subject. So displays. Opla. Yep, seems good. Let's do a whiteboard. And let's take the whiteboard. Here. Can you guys see the whiteboard?
Yeah,
Oh.
we can.
But the iPad closes every time. Hopefully this will work now. Okay, let's try. Okay, it seems good. And I will need these two here. These, I don't need them here. Okay. All good. So as we said, what will happen is selective search takes an image. Selective search will propose a certain region inside the image. Like this. This is the, for example, the region that selective search has proposed. What we will do is we will take this big image, the first big image, right? Send it through a CNN and it makes it smaller, right? This is just a CNN. And I'll do this operation one time. This operation leads to a convolutional feature map. So let's draw the convolutional feature map. I'll draw it with black like this. And one thing to note about the convolutional feature map is it is small in terms of width and height, but it has a lot more channels. So let's say 512 channels. And here it is 40 by 60. Whereas the input image was, let's say, 1000 by 800. Like this. Now, the goal is to basically find the mapped version from the initial proposal in red into a location in here. As we said, this happens with a simple division, very direct. Now, as I said like a couple of minutes ago when we were seeing the RCNN family, we said that the selective search would give us different shapes and sizes, but the actual neural network requires a fixed input. So the actual neural network requires a fixed input for the RCNN and also for fast RCNN, right? So here, selective search could give us a rectangle, could give us a horizontal rectangle, a vertical rectangle, a big square, a small square. So there are different shapes and sizes up to the selective search. What will happen is we must convert all of these. So something like this, we must convert all of them into the same shape. This is the accepted shape of selected search. The accepted shape for our CNN, sorry. So the rest of this one will be just, let's draw it, a classifier. So classifier plus bounding box regression, which is just basically a fully connected neural network. Okay. Now, how do we do this operation? So this operation is called ROI pooling. And what it does is it converts all shapes, all sizes into the same one. So if we had a small rectangle like this, it will convert it into a big rectangle. And if we have a big rectangle like this, it will convert it into a same small rectangle. How does it do that? Let's see. Let me clean up a little bit. And now we will see what the operation does in mathematics. So let's say I have this. Opla. This is my input. And I want to convert it into this. Just this. Imagine I have the following numbers. I'm not sure if I can zoom in. Can you zoom in here? No, you cannot. Okay. I have 2, 3, 4, 5, 6, 7, 8, and 9. This is going to ask questions from you guys. I'm going to expect you guys to answer all of this, but what do you think the number in here should be? Just logically. Similar to, for example, max pooling. What would max pooling do? Anybody? Give a guess.
I think it's take the central number. I'm not sure. Like reduce
Central of what? Which region?
4, 5, 6, 7, maybe.
So this point here, which is the top left corner, it should be representative of the top left corner, right?
Yeah.
How many pixels should it take into account? So here there are 2 pixels, and here there are 2 pixels. The problem is here there is 2, and here there are 4. So how can you split these pixels across these?
I think it can't billing, and we should take like split it again, yeah, in this way, and then calculate each cell average value.
Average or max, as you wish, right? So here, what should we put? We could put either 3 or we could put 4, as max pooling does, right? Here, what do we put? We put 5. Here, what do we put? 8. And here, what do we put? 9. Let's do another example. And it must be converted into a 2 by 2. So how many pixels do we have here? 1, 2, 3, 4, 5. How many do we have here? 1, 2, 3, 4, 5. 5 is not divisible by 2. So how can we solve this problem? How can we do the division? So here it's easy, right? This pixel, it should represent the top left part of the image. To simplify it, we should make the top left part the biggest. How many pixels should it contain? We can't split.
3 by 3, maybe.
We cannot split in half, right? What we could split is either here or here. But as we said, we will make the first part the biggest, so we split here. And then vertically, we do the same thing. And boom, this is how we convert. We take the maximum of this region, put it in this pixel. Maximum of this region, put it in this pixel. Maximum of this and maximum of this, and put it in their locations. Now, as you can see, previously with max pooling, we had a fixed size window, right? 2 by 2 window, we move this 2 by 2 window, we slide it, and we get the output with different shapes. If we have an input that is 8 by 8, the output will be different from 16 by 16, right? But here in ROI pooling, we don't really care about the input size. We're always going to have the same output, regardless of what input we're getting. And we're no longer going to have a kernel for ROI pooling. No kernel. There's no kernel. What we'll be doing is splitting the input based on how much output do we want, right? So if we have 2 by 2, we split the output 2 by 2. If we had 3 by 3, we would split the input by 3. Does that make sense? Mm-hmm. So if I ask a question, why do we apply ROI pooling?
So we can fit it into a neural network.
Yes, so we can fit any region of interest with different shapes into the same neural network. Neural networks, they expect the same size, so we cannot just put the input images as they are. We must always resize them. Or when it comes to regions of interest inside the feature maps, we must always resize them also. So this is the why. The why is easy. The how, as we said, it's just basically a resizing operation. This is how, for example, if this was an image with an image, it will be just a basic resizing. And how do we apply that? Taking the maximum over a customized split. And that's it. This is how we do the ROI pooling operation. I hope this was a little bit clearer in terms of expectation on how does this operation work. Now let's go back to the lecture and we will see it in practice. All good. So as we said, the first part, selective search, does the searching and then it proposes a region. So this is the ROI proposal. ROI proposal will get mapped directly to the feature maps using a simple division. So there's no math happening here. There's no calculation happening in this operation. And then the region of interest that is in the feature map would get sent into ROI pooling and basically standardized into the shape that the neural network expects. We also already spoke about this one, saying that RCNN was very, very slow because of the 2000 CNN passes, whereas the fast RCNN is only slow because of the selective search. So the next operation is working on removing selective search. So before I go into detail or not, can somebody tell me, did we go too much into the details of selective search, or did we just like go through it very quickly? The region proposal networks.
I think in detail, if you have time, you can manage the lecture.
Okay, so let's go in detail. I do remember that we went through it very quickly because we ran out of time, right? Let's just go as many details as we can, and then because the YOLO is going to be fast. So now the architecture is very similar to what it was before, right? So this is the fast RCNN network. It did not change at all. Fast RCNN is the same. The only thing that changed is selective search. We replaced selective search with a concept called region proposal networks. It's a neural network that is very, very basic, and it replaces the selective search operation. How does it do that? Very, very simple mechanism, which is region proposal networks. Let me take, I think a drawing. Yeah, drawing would be much better for this one too. Let's bring it here. All good. Yep, let's bring this back here too. And let's get it. So the operation that is happening here is exactly similar to, remember that first algorithm we proposed in the start of the lecture, the sliding classifier. Exactly the same thing is going to happen here, but instead of sliding on the image, we're no longer sliding on the image like this. We're going to be sliding on the feature map, the convolutional feature map. So here, we will slide a classifier at this place, a classifier at this place, a classifier at this place, classifier at this place. And we will be splitting the image in this manner. So first thing is, this was 1000 by 600, so it was very big. Sliding a classifier on all of these pixels would be very slow because we will slide it lots and lots of times. Plus, there is a problem here, which is when you're sliding on the image, each one of these parts would go into the CNN. So how many times will it take? Let's say 2000 parts by the CNN, so it's very slow. But when we do one pass through the CNN, just one time, get a convolutional feature map, and now we will be sliding first on much smaller size. So we will apply it only, let's say 100 times. It's going to be a little bit more, but let's say 100 times. And these applications will not contain any CNN. So they will contain only a classifier like this. This is how the classifier looks. We will explain later why do we use these 3x3 convolutions and then followed by 1x1 convolutions and then the classifiers. But for now, imagine all of this as just the classifier, something very basic, nothing complicated here. Let me replace this like this. So all of this is the classifier. We will be what is it called? Sliding it over this feature map, the convolutional feature map, and try to predict if there is an object or not. So here the prediction is object or no object. Unlike with the classification part where you are classifying this is a dog, this is a cat, this is a horse, in this state region proposal network, only thing you're predicting is there an object or is there no object? So all the classes are the same for this architecture part, for this part so far. Now, as we said, there are different shapes and sizes for the objects. So every time that we are sliding, we will not just be sliding one rectangle or one classifier, we will be sliding multiple. So let's look at these multiples. The first one is a simple, simple square. And then the second one is a horizontal rectangle. And the third one is a vertical rectangle. So already we can predict, so if we slide all of these three classifiers, let's say, if we slide all of them, we are able to find different shapes of objects. Remember, we will be fixing the shapes later on through regression or bounding box regression. So here in this part, we will fine tune it. So let's say previously it was like this, and we say it's a little bit thinner. So we will be fixing the shape later on, but it will just be a small modification, not a major modification. So here we have, as we said, these three shapes, but there is a simple problem. This problem is if we say this shape like this, it will be mapped to an object of this size. This is the maximum it can get. But what if there was a much bigger object in the image? What if the image contained a large object? How can we fix that? Simply by applying multiple sizes of these same anchors. Like this. So this is for the small objects. This is for the medium objects. What if there is an object that is even bigger, right? So how do we do that? By applying the large anchors like this. And these are the different anchors that we have in our object proposal network or region proposal network. So as we said, the anchors would be mapped to something like this. So when we are at this point A, when we are at point A in here, you see it, we will be applying the yellow anchors on, remember, we are applying these yellow anchors on the convolutional feature map. It is not being applied on the actual image. So the search is happening here at this location, convolutional feature map. But it is the same as searching here. So it is kind of similar to when we apply a anchor of this size, it is as if we are searching in this size. Okay, so the image right here is just a just to help you understand what we are searching for inside the convolutional feature map. So here, for example, the largest horizontal object, which is here, that we applied, was able to fit the human perfectly. So here what will happen is we will fine tune it, basically making it a little bit thinner, like this, let's say, plus we will be classifying, saying that the classification is a object. All of the others, so for example, this one here, it does not fit the input object correctly, so we will say it has no object. And that's it. Now let's move a little bit further in the lecture, and we will see these objects interacting. Let's go. So these are the objects that we spoke about. Their names are anchors. The classifiers that we are sliding, their name is called an anchor. This sliding window that goes over the convolutional feature map, its actual name is anchor. This is how we will be referring to it from now on. The name is anchors, and as you can see, there are K anchors. For our case, in the FastRCNN example, there are 9 anchors, but it depends on, for example, there are different versions of YOLO, which use different numbers of anchors, and some of them, they allow you to bring in your own anchors, right? You fix the sizes of the anchors yourself. So it's not just about the number, but also about the shapes and everything that relates to them. You can do it yourself. So these are, as we said, the anchor boxes. They are very simple, square, horizontal rectangle, vertical rectangle, and then we go bigger square, bigger horizontal rectangle, bigger vertical rectangle, the biggest square, biggest horizontal rectangle, biggest vertical rectangle. So these are the 9 anchors that we can use in our region proposal network. And as you can see, they first go through an intermediate layer. This is just basically a mapping, or let's say, let me get some annotation. Yeah, so this part is just here to to bring in some extra non-linearity in the learning, so something that is learning well, and then it gets splitted into 2 parts. The first part, as you can see, it has 2 times 9 or times k, 2k layers, and this one has 4 times 9 layers. So can somebody tell me what this one does? Why there is 2 in here and why there is 4 in here? Classification, regression. So why there is 2?
In classification, we just have 2, like yes or no, and in
Yes,
regression, we have more
object,
parameter.
no object. And in the case of the 4, what are they? So these 4 are, what we were saying is the improvement of the anchor box. These will provide us a much better fit of the objects that we're looking for compared to these anchor boxes. So now if we go back, not sure if I can zoom in. Oh, I can zoom in. Nice. How do I? Okay, like this. So here, for example, we first pass by this. So here what we have is a extra convolutional layer that will help us basically do a little bit more learning, and it will contain a 3x3 filters and 512 channels. So the number of channels is the same. Whereas here, so here what we will happen is we will have a set of 1x1 filters, same thing on top in here also. And they will have how many units? 18. Basically, how many kernels? 18 for this specific number. Let me simplify the 18 a little bit. So here, instead of 18, look at it as 9 times 2. And instead of the 36, look at it as 9 times 4. So now can somebody tell me, why did we use a 1x1 kernel that has a 18 or 9x2, 1x1 filter, and the layer contains 9 times 2 kernels. Can somebody tell me why would anybody use a 1-by-1 kernel? Convolutional filter. What is the main goal of using these things? Because they do nothing, right?
To
It's just
get more details, maybe
get more details or less.
from feature map.
Yes, it's about getting less details from the feature map.
Okay.
Yes. So here, as you can see, we went from 512 channels to how many channels? 80.
Okay.
So we're aiming for getting less details, right? We're keeping the same size of the, what is it called? Width and height, but the number of channels, we're reducing it drastically such that it fits the shape that we want. This shape is more interpretable by us, right? Because it has 60 and 40, the same as the convolutional feature map. But the number of channels here is exactly what we want. So the number of channels is a number that is interpretable by us, which is 18. This allows for the calculations to be extremely parallelizable and at the same time, extremely useful for us, right? Because they contain the following information. For each one of them, we have 9 by 2. So we have 9 anchors and their 2 results, basically whether there is an object or not. So this shape allows us to do what we were looking for, which is the attributing a class objectness score to each individual anchor by using this multiplication. The shape is very useful for us. And from there, this shape is being applied using CNNs, making it extremely parallelizable and allowing us to do this whole operation extremely fast. Same thing upside for this 36, right? This 36, so the 36 is 9 times 4, and we're seeing it here. So here for each anchor, we have the ability to put a new X, a new Y, a new width, and a new height. This allows us to fine-tune the actual shape of the object compared to the anchor that proposed it. And this is basically it. How do I? Okay, let me see. How do I unzoom? Opla, nice. Nope. Yes. Okay, how it works. Yeah. So this is basically it for the region proposal networks. It's a very simple architecture that takes in a pre-trained VGG network. It is going to be the same VGG network that we will be using for the fast RCNN. It creates for us a convolutional feature map. This is a convolutional feature map. On top of the convolutional feature map, we will be applying multiple anchors. How many anchors exactly? 9 anchors, or here is 9 anchors. Each one of these anchors would contain a classifier and a regressor. The classifier is only an object classifier that separates things into foreground and background. It does not separate things into cat, dog, horse, human, stuff like that, but only background / foreground. So this is the task for the classifier. For the regressor, it will show us dx, or the improvement over the x, dy, which is the improvement over the y, d height, which is how much should we change the height of the anchor to fit perfectly the object, and then dw, which is how much should we change the width of the anchor to fit perfectly the object. And then from here, we go with region proposals. So these are the proposals that we get, similar to fast RCNN, we send these region proposals through ROI pooling, and then ROI pooling would give us always the same size. So here, as you can see, one is big, one is small, one is rectangle, one is square. All of them will be converted into the same size after ROI pooling. And then after the ROI pooling, we have one couple common layers for fully connected layers for improving and basically getting some non-linearity in there. And then we have one layer for classification, and then another one for the regression. The classification is going to be built using cross entropy or softmax for classification, basic loss function for classification. And for bounding box regression is just a regression task, right? And the loss function we will be using is L1 loss. The major loss that you guys are used to working with is mean squared error. But now for this task, we are using the L1 loss, which is just basically mean absolute error. Not major differences, but this one provides more, let's say, more accurate results. Well, because it doesn't exaggerate basically when you are very far from the object itself, and it does help getting more accurate numbers, like very, very close to where they need to be. So this is it for the RCNN family. We spoke about RCNN. RCNN uses selective search, and then fast RCNN still uses selective search, but here instead of 2000 passes through the CNN, we have just one pass through the CNN. And then from fast RCNN to faster RCNN, we removed selective search. So we'll no longer have selective search. We have one single RPN network, and then we have one single pass through the CNN. So one CNN is the same, but here, from here to here, we removed selective, let me use this. So from RCNN to fast RCNN, we reduce the passes through the CNN by going from 2000 to only one pass. And then from fast RCNN to faster RCNN, only thing we did was we removed selective search. So that's it. For BASC RCNN, we will be seeing it on the next lecture with the segmentation tasks. All good? All good.
Yes.
So now let's go to the part of the lecture that we want to see. As we said, we spoke about object detection in general. We spoke about intersection over union. We spoke about non-maximum suppression, RCNN. Sorry. Fast RCNN and faster RCNN. So probably during the lab, you have already worked with Detectron. So Detectron is a library from Facebook that allows us to basically have access to multiple implementations of computer vision models. So in this what is it called, library, you will find fast RCNN, faster RCNN. You will find mask RCNN, and hundreds of other architectures already pre-trained. You will find fast RCNN pre-trained on ImageNet, fast RCNN pre-trained on some other neural network, fast RCNN pre-trained, all the kinds of like architectures that you might want with all the kinds of pre-trains that you might think of. So it's a very big data, big library that contains lots of very good pre-trained models, already implemented architectures, and a very good or easy to use, let's not call it an API, but like easy to use interface on top of these models. It is fully written in PyTorch, which makes it extremely flexible for any research purposes that you want. So for example, if you want to go from the model that does the predictions, so go from predictor, and you want to access the actual weights, just put .model, and this would give you access to all the weights. So .model, dot, let's say, first part, which is RPN, right? So this is the region proposal network. If you want to go to this first CNN that is inside it, it's usually either VGG or something, dot VGG, dot CNN1, dot max pooling. If you want to change any of these, if you want to get access to their weights, if you want to get access to their, what are they called? To their gradients, if you want to access their the output, their convolutional feature maps, anything that you want to access, you can easily access it as if it was written in basic Python, right? So it's usually built on top of PyTorch, which gives you extreme flexibility to access any of these values. So as we said, just go from your predictor class dot model, and there you go. You have yourself the PyTorch model that you always, I think you at least have some familiarity working with PyTorch models. It provides trained models for a variety of tasks, as we said, object detection, hundreds of those, object segmentation and panoptic segmentation, dense pose estimation, landmark detection, and much, much more. Now let's go to YOLO. So YOLO, the first part, or I think we could take a break before going to YOLO, right? Yeah, but let's just at least give it the name. So YOLO, the name is very simple. You only look once. Now, a small question. In the faster RCNN architecture, here, how many times will you be looking at the image? Once through here and once through here. And you will be doing the classification first here for background versus foreground, and you will do it again here by doing, what is it called? The classification of the object. So once you will do the classification of objects, of objectness, and then the classification of the actual class. So you will be doing it twice. This is the major difference between fast RCNN and YOLO. YOLO does not look at the input image multiple times, but only looks at it once. And if we want to understand YOLO, let's first ignore everything and only look at this first part. The rest of it will be easy to understand. So let's take a 5 minutes break. And after that, we come back, we explain YOLO really quickly, and then we go to explaining what mean average precision is and how we can calculate it manually. All good?
Yes, sir.
Nice. So see you at, let's see you at 10. Yeah, see you at 10. All right, so let's finish, as we said, the YOLO part of this lecture. Let me try to zoom in here. I cannot zoom in. Oh, wow. Ah, okay. Oh, so let me just connect the iPad again. Let me configure it. Done. Let's see. Okay. And okay, all good. And then I just scratch it like this. And we're good. Yep. So what ends up happening in the YOLO architecture is very simple, right? You take an image pass it through a couple of CNN or convolutional layers, very basic, right? And then these convolutional layers will be passed, or these images, sorry, so image goes into a convolutional feature map, convolutional feature maps, convolutional feature map that is much smaller, convolutional feature map that is much smaller, smaller, until we arrive here with the stride equals to 32. What does stride equal to 32 mean? Very simply, that the size of this image is 32 times smaller than the input image. So if I ask you a question, let's say we already had a very tiny object in the input image. We had a very tiny object in the input image. And then we shrink it by 32 times. So we make it 32 times smaller. Is it still detectable, right, in this image? Can we still see it by your human eyes?
I think we can't see.
We cannot see it, right? So what are the only objects that we can see? Here, imagine we had a very big object like this one, and we shrink it 32 times. Is it still visible? Can we still detect it? Can we still see it for a very large object?
Yes, I hope
Yes.
so.
Of course.
Yes. So the first part of the YOLO architecture is built to basically find large objects. How it does that? Very simple. It takes the input image and pass it through convolutions and convolutions and convolutions, and it arrives at this convolutional feature map that is specifically built for large objects. We will see how it does the classification later, or how it does the bounding box regression later. But for now, only thing that we care about is it takes an image, pass it through a couple of convolutional layers, and then from these convolutional layers, it does the predictions or does the detection of the large objects. So let me clear this and let's go back to the bigger picture. How do I go back to the bigger picture? This is gonna be hard. Okay, done. And here is the rest of the architecture. So as we said, the first part is it makes it extremely small and looks for the large objects. And then it goes back, not from here, but let me, how do I do this? How do I clean it up? I don't know. Like this, but where is the, okay, here it is. Let me clean this. Yep. So, and then from here, let's imagine that this size is a little bit small. So this is like 32 times smaller than the input image. Sorry. So this is 32 times smaller than the input image, and we apply the upscaling. Do you guys already know what upscaling is? The upscaling operation.
Something about making image bigger in amount of pixels via some operations mathematically.
So let's say we had a 2x2 image like this. It had 2, 5, 5, and 10. How do we make it? We make it much bigger like this. Very simple. Put 2 in here, 5 here, 10 here, and then 5 here. And then basically build the values between them. Between 2 and 5, let's put 3.5. Between 2 and 5, 3.5. 5 and 10, let's put 7.5. 2, and then we put the 5 here, and then here we put the 7.5. So this is what upscaling does. It just simply allows us to make the image bigger. One second. It makes the image a little bit bigger. So previously we had a 32 times smaller. So when we make it a little bit bigger, what does that give us? Well, let's say twice as big. It becomes of stride of 16. So here it goes from stride 32 to stride 16, meaning it doubles its size. One second, I'll just have to fix this issue. It's nice to teach with an iPad, but it has lots of problems. Let me try. Okay. So as we said, it's pretty direct. What it does is it basically makes the input image a bit bigger. So the first part of this one, we're looking for the large objects. When we make it a little bit bigger from a 32 stride to a 16 stride, again, this is just a couple of convolutional layers, nothing interesting happening here. What we're able to find is a convolutional feature map that is 16 times smaller than the input image. 16 times smaller means that the large objects are still visible, but what's the best object that is most visible is the medium size. Medium-sized objects are extremely visible, and they fit perfectly the types of anchors that we will be using at this location. Next, from here, we go from 16 times, upscale it up to 8. So we double the size twice, pass it through a couple of convolutional layers, again, couple of convolutional layers, nothing interesting happening in this place, and we get a stride of 8. Stride of 8 means it's optimal to find the smallest objects, and this is where we do the small object detection part of the YOLO. So here we have large, here we have medium, and here we have the small. And how we do that? Why do we first do that? Why do we first start with detecting large objects and then medium objects and then small objects? Why not just detect small objects first and then continue the convolutions? They make the objects smaller and then do the medium and then do the large. Why do large and then upscale and then medium and then upscale again and then do this the small? So this one is just to help basically the neural network to learn what are the components of the image. I don't know where the annotation part is. Here it is. Okay, got it. Let me bring it here. So now what we said is we first do the large objects, or we start by predicting large objects first because it gives us a bigger picture about the components of the image. So basically now at this stage, we're able to understand what the image contains, right? There is a big, let's say, big human over there, and there is a car. And then for the medium sized, where there is a baby next to the human. And then for the smallest size, there is a backpack behind the human. So basically it allows us to first understand the largest part of the image, understand what's happening inside that image, and then we go into the details. This is the only reason why we have this order: large, medium, small. Although it makes the training slower, right? Because you have a lot more convolutional convolutional layers here, and a lot more upscaling, which is still going to take some calculations. but it does provide better results because now you're able to see the bigger picture first, and then go into the details. If somebody is here interested in doing, what is it called? In doing a project about YOLO to make it faster, he could try to inverse basically these parts and remove the upscaling, and that should give you much faster results or much faster version of YOLO, but it will give you worse results, less performant numbers. It could be something interesting. It could be like a reason to publish a paper about it. It's quite nice of an idea, and it could be also, if I'm not sure you guys are like masters first year, right? You guys are first year masters?
Yes, we are first.
Yeah, so it could be like the master's project for you. So it's something that you start right now, you do some work on it, publish a paper, and then from that paper, you start doing some research on it. And basically by the next year, you would have your master's thesis already finished before you even start the second year. So this is something that I highly encourage you guys to do. So if you are going for like a master's and you want to get like some good results, preferably finish your master's thesis in the first year, and in the second year, try to get like a job or something, like part-time job. It really helps. So this is YOLO, very simple architecture. First starts with large objects, then it goes to medium, and then it goes to small. The architecture contains lots of basic convolutional layers plus upscaling layers. We have seen what upscaling layers are. Now the last part of the YOLO architecture is to understand the final detection part. So this, what happens at each scale, what is happening? So here we will see exactly what is happening. At each scale, so at each large, medium, and small scale, we will be applying the following calculations. Prediction box, this is the number of channels of the last convolution layer. So as we said, this is a convolutional feature map, and we use it to search for the objects. And how do we do that? Simply by setting the number of channels equal to the following structure. The following structure contains the following, right? So first is Tx, Tw, Ty, Th, meaning the improvement over X, the improvement over Y, the improvement of W, and the improvement of the height. This allows us to find the best coordinates for the object. And then PO, which is the probability of being an object, is the objectness score. Remember of, what is it called? I forgot the name. Region Proposal Network. So Region Proposal Network was saying, is it a background versus is it a foreground, or is it an object? Here, we will be doing both this. So this is happening here, plus the classification, which is class score in here, meaning number of classes. So this is what the major difference between YOLO and RCNN is, or faster RCNN. Faster RCNN was doing the background versus foreground detection first, and then doing the classification at a second location. But YOLO is now doing both objectness score and classification score at the same time. You only look once. Now, this formula is extremely important because it's something that you must write by hand. For example, if you are training a, what is it called? A model like, what is that called? YOLO V4. If you're training that, you will write by hand in the configuration file this formula. You must write it. classes, number of classes, plus 5, which is 4 plus 1, times 3. And this times 3 must be done for the large, for the medium, and for the small layers. Now, why do we do times 3? Can somebody explain to me why times 3?
3 channels.
For what? Is it for the size? Or is it for the shape of the anchor? So these are anchors. Why do we do times 3? Yep. So this is the time 3. 1 is for a square, 1 is for a horizontal rectangle, and 1 is for a vertical rectangle, so that we can find objects of different sizes and forms. And that's it. This is basically it for YOLO. YOLO is a very simple architecture, direct, very direct. This is YOLO v3 architecture, but as you might have noticed already in the lab, YOLO v4, YOLO v5, YOLO v6, YOLO v7, and YOLO v8 all follow the same architecture. There are some improvements in the image processing. So for example, they do more data augmentations. There are other images which, or there are other architectures which use, for example, instead of ReLU, they use a different activation function, but all of them are almost the same architecture. Some of them, they remove this medium scale and they just do large versus small. And that basically is a neural network that is much faster and much smaller. So it could go, for example, into your what is it called? To a mobile phone, right? You can upload it onto a mobile phone and do the predictions from there. But that's basically it for YOLO. So before I go to the part of the lecture which is speaking about mean average precision, I would like to remind you guys about the project. So hopefully after 2 weeks from now, you will be doing your project presentations, not final project presentation, but intermediate project presentation, meaning you will be giving us like a sneak peek into your project, some code, some execution, maybe a data set, something that you've already started, telling us we are facing this problem, this problem, this problem. And for the final presentation, we will try to build some sort of interface, or we will try to build a better, more powerful model, train it much longer, do some hyperparameter tuning, stuff like that. So hopefully you will be doing this after 2 weeks, as I said. So please start preparing or start working on your projects. You can work in groups of 2 or 3 or 1. And yeah, the projects are up to you. You can choose any project that is doing computer vision. You can do object detection. You can do anything you guys actually want, as long as the project is a little bit more challenging than just copy pasting from the internet. Which means that copy pasting from the internet is completely allowed, totally free. You can use any code that you find on the internet. You can use ChatGPT, use anything you want, as long as you give some good results or good models or good project or good ideas. Okay?
I have some question about this. For example, I have idea with football players tracking.
Yes.
And some statistics, some other features. And for tracking, I'm using ByteTrack, and I didn't honestly understand how does it work, but it worked. So can I use this?
Yeah,
because it's provided library on GitHub.
Yeah, of course.
Okay, thanks.
You're welcome. Anybody else has other questions for the project? I guess we're good. So let's go to the final part of the lecture, which is about objectness, or basically object detection and performance evaluation. So how do we evaluate an object detection model using mean average precision? I'm sure you have seen it somewhere in the lab, but how do we basically build this score? First, the The first word that you guys are seeing here is the word precision, which is a word that you guys are already familiar with when you speak about basic classification. So the task in here that we're using is to convert an object detection problem into a classification problem. We will see how do we do that later during this tutorial. And it's a very simple tutorial. So basically, first we go from the predictions to the class score, and that gives us from this to this. So that gives us basically our accuracy, right? So we can see our accuracy based on from the predictions and the actual classes mapping. We get our true positive, our false positives, true negatives, and our false negatives. This is for a basic classification task. No object detection is happening here. From there, we can build our precision recall curve. So the precision recall curve, I'm sure you have already done this with Professor Khan. Basically, you will be changing the thresholds for the classification, right? These are the thresholds. Remember, for going from what is it called? Prediction score of 0.7, this means it's predicted positive because we assume that the threshold is 0.5. Anything higher than 0.5 means that it is positive. Anything less than 0.5 means that it is negative. But this does not always hold. So for building this precision recall curve, we will be using multiple thresholds. Not sure where they are. Yeah, we will be using multiple thresholds. We will start by a threshold of 0.2. Anything that was predicted less than 0.2 is class 0. Anything that was predicted above 0.2 is class 1. And of course, we will have error that is extremely high on these two extremes. And the 0.5 would have the lowest error or the highest accuracy. And here, when we walk through these different thresholds, we will get a different precision and recall at each step. So at step 1, we have this kind of precision and recall. Step 2, we have this one. Step 3, we have this one. Step 4, step 5, step 6, and step 7. This is something that you're already familiar with seeing. You're already familiar with knowing what F1 score I am assuming. Now, the next step would be in the area under the curve. This is also something that I'm guessing you already knew. Area under the curve is just basically the area that is being trapped under this curve. The higher this area is, the better your model is. The lower it is, or the smaller it is, the worse your model is. So this is what we call the area under the curve. Another way to see the concept of area under the curve is average precision. So average precision here looks like a very complex concept, right? So what we're doing is we're summing the precisions. So we're summing the precisions, and we multiply each precision with a difference in the consecutive recalls. So it's a very complicated concept, as you can see, but it's a very simple one at the same time. You're multiplying the precisions, so summing the precisions, and multiplying them by the difference in consecutive recalls. So here, for example, we are at this, let me get zoom. I don't know where that, here it is. Let me come here. Okay, right. So we're multiplying this by these. So what does this give you? It basically gives you this area, right? And then we multiply this by these, by the difference in the consecutive recalls, and it gives you this area. We multiply this by these, and it gives you this area, and the same, and the same, and the same. So it's kind of an estimation of the area under the curve that is a bit faster than the actual area under the curve calculation. So this is average precision. Average precision is just basically a calculation of the area under the curve that is a bit smoother or less smooth than the area under the curve. It's a very simple concept that allows you, you can think of it as just F1 score, you can think of it as whatever you want, but for now, this is how we do it. Not sure if you guys will see it again in the lab in more detail, because the actual formula is quite simple. The actual idea behind it is also very simple. But as we said, this is the average precision, which is a classification evaluator. How do we use it for an object detection problem is through the intersection over union. So what we do is we take this actual bounding box, we take the predictions, and we calculate the intersection over union. If the intersection over union is high, then we classify this as a true positive. If it's not high, we calculate it as a false positive. And that's it. So now you went from a object detection task using intersection over union into a basic classification task, which is true positives, false negatives, and true negatives. And this should allow you to basically do the same task again of, what is it called? Of mean average precision, right? So you will be taking the average precision for each class using the intersection over union, convert this object detection problem into a classification problem. And then for each individual class, you will be doing that. Each individual class will have an average precision. And for all the classes, you will just basically take the mean across all the different classes. And that gives you the mean average precision. So mean, the first mean is mean across all classes. Average, which is the second average, it means average across all the recalls. And precision is just basically precision. So we're basically taking the precision, averaging it across the different recalls at different thresholds, and then we take the mean across different classes. And how do we use this idea that is a classification idea on a object detection idea? Using the intersection over union by simply converting, if there is a high match, then it's a positive. If there is a low match, then it's a negative prediction. That's all we have. That's all we will be checking for this one. You could check mean average precision, the tutorial, look at it much more deeper. And if you want to get a revision about something like a fusion matrix, accuracy, and recall in more depth, then this is a good tutorial. I will be sending these over the chat. So if you have any questions, you could just look at them. Do you guys have any questions? Okay, nice. So get ready for your lab, and don't forget to start working on your projects as soon as possible. Huh? Good luck, everybody. See you soon.
Goodbye.
Bye-bye.
Thanks, bye.